Hello my friends and welcome back to the You Can Do TV channel. From the first plans to the last steel beam, Genova's new bridge demanded unwavering focus. Hundreds of workers coordinated like a single organism, each step crucial to the outcome. Piers grew rapidly, finished in under 8 months, while metal sidings were prepared for hoisting. It's wild to see a single steel span stretching over a kilometer take form so quickly. By October, positioning began under the watch of Prime Minister Giuseppe Conte, carefully setting each piece atop the piers. After 10 months, the bridge dominates the Polcevera Valley horizon. This is what teamwork and determination look like in action. Italy regained a structure that is both smart and sustainable.
The South Approach Viaduct Segment 2 of Izmit Bay Bridge is carefully lifted using heavy-duty lifting ropes, supporting 400 tons of structure. Impressive to see a single segment handled this way. Each 400-ton piece is aligned with precision before final securing. Coordination between operators and engineers ensures stability throughout the lift. The segments are then bolted and welded for permanent placement. Never thought a single piece could weigh this much. Continuous checks monitor safety and alignment, keeping the massive structure on track for completion.
Workers and heavy machinery tackle the steep inclines of the new Aso Bridge in Kumamoto, a symbol of post-earthquake recovery. Prefabricated segments are lifted and positioned using self-climbing systems, reducing scaffold assembly time. Reinforced concrete piers rise up to 97 meters, while rail climbing devices transport formworks and rebar efficiently. The scale of these towering piers is insane. Concrete is poured continuously, including the central closure section, using cantilever construction methods. Over 24-hour shifts, large mobile work vehicles handle oversized materials. One can't believe how coordinated everything has to be. By combining prefabrication, climbing systems, and round-the-clock labor, the project cut construction time by roughly 1 year and 4 months. Every segment ensures the bridge will serve as a safe and lasting route for vehicles and pedestrians alike.
Large bridge blocks for the Daishi Bridge renewal move across Tokyo Bay in a controlled water transport run, showing how each oversized steel segment is handled with confidence. The PAP-5 block is prepared first, positioned on a barge to maintain balance while crews coordinate with tug operators. That steady push almost feels like the barge is guiding the block, rather than the other way around. As the P3-P6 block is secured, support frames lock it tightly so the segment sits level for the long route ahead. A quick check of lashings keeps everything stable as cross currents shift lightly under the hull. The next action involves shifting the P8-P7 block using synchronized tug movement, keeping its nearly 300-meter alignment plan on schedule. Crews check clearances along existing bridge spans, planning routes to avoid interfering with the current structure. Didn't expect such a huge block to glide this smoothly over open water. With the P5-P5 block positioned next, tide timing becomes crucial for gaining ideal draft. During mid-route adjustments, teams communicate to maintain barge orientation while crosswinds build mild drift. Feels like the whole setup knows exactly where it wants to go. Approaching the delivery point, operators slow the tow to stabilize the P4-P6 block before docking hardware engages. A brief pause helps match angles between the block and the receiving platform. Final alignment ensures each transported segment fits its designated point in the Daishi Bridge update plan. That moment before the block settles almost feels like the project is taking a deep breath. The scale of coordination shows how large segment transport can move smoothly when timing and control stay tight over the entire route. The completion of this water transport stage highlights how each block's journey supports the broader renewal effort across the expressway's vital corridor. Across the MRT Malaysia worksites, engineers and crews coordinate with TBM systems and elevated equipment to shape tunnels and guideways. The system's impact is visible not only in its scale, but also in the steady progress made at each station and tunnel section. You notice how every segment connects smoothly once the structural stages meet? The video follows the creation of a fully functional rapid transit backbone meant to handle heavy daily usage while easing movement across Greater Kuala Lumpur. That sense of momentum feels almost like the whole corridor is pushing forward on its own. The excavation phase uses tunnel boring machines designed to maintain pressure and stability while carving through Kuala Lumpur's mixed geology. Operators guide the TBM to secure the face while crews at the rear manage pipe jacking, slurry transport, guidance systems, and segment installation. The first action in underground works involves positioning the TBM so the cutter head can engage the prepared entry point, followed by steady advancement and continuous lining of the tunnel with precast segments. Many trainees from the Tunneling Training Academy participate in these works, gradually gaining confidence as they operate piping systems, segment erectors, and support equipment. Some of them mention how each completed ring boosts their sense of progress. Above ground, elevated guideways take shape through sequential launching. Beams are lifted into place using specialized gantries that distribute weight evenly as the span is secured. Once the superstructure is stabilized, crews install track plinths, power rails, drainage elements, and walkway brackets. Later tasks include signaling mounts, emergency access fixtures, and electrical containment. That long stretch of guideway almost grows quicker than you expect on an urban skyline. Station construction progresses in defined layers. Structural works consolidate columns, concourse slabs, and platform levels, followed by architectural fit-outs such as wall panels, glazing, tiling, and ventilation housings. Subsequent installation activities include escalators, elevators, communication rooms, ticketing zones, and platform screen doors. Some stations show modern styling with bold geometry and bright circulation paths, giving each location its own identity. That clean layout gives off the feeling that commuters will instantly know where to move next. Emergency drills are conducted repeatedly at various points of completion. These sessions coordinate fire response teams, station controllers, evacuation supervisors, and tunnel rescue units. The first drill in each location rehearses positioning responders at access portals, while later drills increase complexity with simulated smoke, stranded passengers, and suspended train operations. These exercises strengthen readiness and ensure every team understands their part once the system opens to the public. As the line edges closer to completion, test runs bring together rolling stock, traction power, signaling logic, platform screen doors, and operations control centers. The initial movement of a train along a newly energized section confirms track geometry, clearance, and stopping accuracy. Later runs evaluate communications between train, control room, and wayside equipment. You get a small jolt of surprise when the first test train glides through smoothly without hesitation. Public feedback highlights excitement about easier travel between Sungai Buloh and Kajang and relief at avoiding congestion. Many note that the line will shorten trips to work, school, and commercial hubs. That kind of convenience hits you when you imagine skipping traffic entirely. The completed system is expected to reduce travel time, expand job access, and support urban growth throughout Greater KL. That idea of more connected daily life tends to stick with anyone watching this unfold. What began as a national priority now stands as a major infrastructure achievement carried by engineers, trainees, construction crews, and the community. A compact pit this large always pushes equipment to prove what it can handle, and the Kubota KX71-3 with the CAT 323D rises to the job as they prepare the pumping station foundation. The first action focuses on clearing and shaping the deep pit so the drainage pump setup can fit securely. Material is shifted in steady runs, and that pole looks tougher than you expect for this size of excavator. Once the layout stabilizes, operators guide the machines to carve the 8x10x12 meter profile needed for the pumping area. As soil layers come off, the workflow settles into a controlled rhythm, and the way that bucket snaps through the dense patches almost feels like a small power flex. The team keeps forming the pit walls to support the storm drain channels planned for the site. It feels like the CAT 323D barely pauses, helping prepare the ground for the drainage network that will handle the area's runoff. A towering crane at Arsesate Stabio leans past its limit, the structure shifting until gravity wins. Hard to miss how fast the tilt escalates. Workers nearby step back as the boom sweeps downward. The frame buckles, hits the ground, and dust lifts in a sharp burst. Kinda feels like the ground jumped first. The crew moves cautiously toward the wrecked sections. Didn't expect the collapse to drop that abruptly. The machine lies twisted, ending the operation instantly. Height pushes construction to its limits on the Chongqing Cliff project, wrapping the new roadway tightly around the mountain while crews secure each tier. Work moves forward by cutting narrow ledges along the rock, so structural frames can sit firmly. Reinforcement grids follow, locking into drilled anchor points to stabilize the turns. Concrete crews then coat each segment to form the continuous cliffside route. When final panels settle in place, the whole bend looks like a giant loop, drawn by a steady hand. Steel sections and heavy machinery carve the path for the Fortescue River gas pipeline. Crews from TransAlta and DBP Development Group weld and lay pipe along the 270 kilometers route. That joint alignment looks tougher than it reads. Sections roll into position, inch by inch, guided by survey teams. The 16-inch diameter pipeline threads through varied terrain towards Solomon 125 megawatts plant. Robotic inspection arms follow each weld, ensuring integrity. That stretch almost feels endless today. Trenches are filled, supports installed, and final testing begins. Gas will flow safely from Dampier to Bunbury, powering electricity generation. The sheer coordination is oddly satisfying. Operators maintain pace, keeping work seamless and precise. Across challenging terrains, precision pipeline crews navigate heavy machinery and large-diameter steel to construct transmission and gathering pipelines efficiently. Auger boring rigs drill precisely under obstacles, while guided wet boring ensures minimal land impact. Teams weld and inspect each steel segment, then carefully align the pipeline for burial. That coordinated movement of crews and machines feels like a ballet of sheer force. Design and planning back every action, keeping environmental compliance at the forefront. Once sections are installed, inspections verify safety and flow capacity before operation begins. You'd never guess how smooth such complex drilling and alignment can look until you see it in action. Generations of craft blend with CNC power at Mario and Son to shape granite slabs. Selected stone is scanned, laid out digitally, then cut. That barcode jump feels oddly quick. Water jet paths guide edging and reinforcement.
What makes Timken Steel's forged rolled bars stronger in the center? Timken Steel's 300-ton forge press presses forward the boundaries of engineered steel production. The massive press applies uniform pressure along the entire length of each as-cast ingot. Operators monitor the heating and soaking of ingots before forging, ensuring consistent temperatures for optimal metal flow. The forged rolled process combines multiple forging passes, compressing the hot metal to enhance center soundness and strength. Each pass visibly improves the ingot's core condition, showing the results of precision engineering. After forging, semi-finished bars are sent to the rolling mill, where size and shape are finely tuned. Large bar inspection lines, including ultrasonic tests, ensure uniformity for critical applications worldwide. Seeing these bars move through the inspection line is oddly satisfying, like the steel itself is proving its strength. The end product, durable, dependable SBQ steel up to 16 inches in diameter. Every bar reflects technical knowledge, reliability, and consistent quality. The combination of forging and rolling yields steel that industries rely on for performance under stress. That engineered toughness feels almost alive in the hands of skilled operators.
Watch molten slag flow into pits as workers keep operations steady in the smelter. That swing of the crane is more controlled than it looks. Workers channel molten slag into designated pits, letting heat dissipate across the cooling ground. Later, slag stockpiles will undergo treatment to recover remaining copper. The sheer scale of molten handling is wild to imagine. Every step ensures material moves safely and efficiently.
Molten metal reaches 540 degrees Celsius as it is carefully positioned above molds in Framatome Le Creusot foundry. Operators control the flow, filling 80 tons of liquid in just 3 minutes while ensuring no turbulence affects the casting. Exothermic and insulating powders are applied to regulate cooling, which can last up to a week before molds are opened. That fill looks smoother than expected for such heavy liquid, almost like it's sliding into place on its own. In the forge, ingots of 150 tons are handled with manipulators and pressed under forces up to 9,000 tons. Each hot forging step enhances mechanical and physico-chemical properties critical for nuclear safety. Operators monitor every phase closely, while hydraulic presses shape components for the primary circuit. Seeing 325-ton capacity lifts in action makes the scale of these operations astonishing. Final machining adjusts dimensions precisely using vertical and horizontal CNC lathes, portal milling machines, and deep drilling rigs. Non-destructive testing verifies conformity before assembly. Every axis, press, and manipulator works in coordination, combining heat, pressure, and precision control. The reclaimer boom weighs 240 tons, yet still must travel delicately on its way to Henderson. Crews secure every segment along the 70-meter length before the haul leaves for Henderson. Keeping the load steady during each shift in terrain. Dual escorts guide the vehicle on tight turns, and one slip here would give anyone a heartbeat jump. The hauler keeps a slow, controlled pace, letting suspension systems absorb each bump across the road. Kinda wild to see something this huge glide like a lazy whale. Spotters walk beside the carrier to signal clearances, making sure the 11-meter width avoids obstacles. The final approach toward the yard feels intense, and the whole scene almost freezes when the transporter squeezes through the last narrow gap. Crews coordinate with pulleys and mechanical lifts to recover wooden boats in the harbor safely. It's impressive how the entire vessel moves in unison, reflecting the skill and coordination of the team. Ropes, pulleys, and the sliding system are synchronized carefully, ensuring the boat remains balanced and intact. Observers notice how the tension and placement of each rope affect the smooth ascent, demanding precise adjustments at every moment. Throughout the operation, communication remains essential. Signals are exchanged constantly to keep the vessel stable. The entire process demonstrates how traditional techniques and teamwork come together to manage a delicate maritime task efficiently. Once fully out of the water, the boat rests on supports, allowing crews to inspect the hull for rot, cracks, and water damage. Even a small misalignment could have tipped the boat, so each move is calculated meticulously. The team discusses next steps, whether for restoration, preservation, or safe disposal, applying decades of maritime experience. The sight of the boat-lifted hull makes you appreciate the scale of effort behind a single salvage operation. By the end, viewers gain a clear understanding of the careful planning, expertise, and respect required to recover a historic wooden boat intact from the harbor.
The DC 210mm cutter spins at 303 RPM, tackling gear modules with remarkable speed. Operators mount P2.1.Z.AN material securely as the DC 210mm cutter spins at 303 RPM, slicing with VC 200 meters per minute. That feed rate handling seems deceptively swift for such dense alloy. Each tooth is shaped with F equals 0.6 millimeters, maintaining tight tolerances. Axial and radial movements synchronize to produce flawless gears ready for high-stress applications. Seems like the machine never hesitates yet tackles every cut confidently. Sandvik Coromant's control ensures repeatability and accuracy. Watching the milling unfold, you might just imagine this cutter chewing through the steel like butter.
How does a container lift and rotate smoothly without spilling its contents at Battellini's training in New Jersey? The NRC Rotator shows the way. Operators guide the container upright with careful coordination, ensuring balance and safety throughout the maneuver. The Rotator's versatility allows each container to rotate and align perfectly without shifting its load. Trainees watch the process, learning control and timing. Even subtle adjustments can prevent accidents on such heavy equipment. The container is successfully placed, ready for transport. Everyone seems genuinely impressed by the smooth rotation and lift. The massive external tank at Kennedy Space Center towers over the launch pad, dwarfing nearby structures. Liquid hydrogen and oxygen, stored in the rust-colored external tank, combine as fuel for the shuttle's three main engines. The calculated venting of oxygen gas signals the readiness of systems under extreme pressure. Solid rocket boosters, SRBs, each containing over 1 million pounds of fuel, provide 83% of the thrust needed to reach orbit. It's striking to imagine the power contained within these boosters, waiting to propel humanity skyward. All crew members are aboard Atlantis, with Commander Kenneth Ham leading the mission, supported by pilot Tony Antonelli and 4 mission specialists. Closing the hatch marks the final checkpoint in launch preparations, and the access arm retracts. The countdown reaches 0, and the 3 main engines ignite, followed instantly by the SRBs. Watching the boosters separate and splash down miles away highlights the precision of timing and engineering. Atlantis rises majestically, carrying its crew toward low Earth orbit. Cameras from multiple angles capture every moment, from the ground at Kennedy Space Center to onboard perspectives. This flight, STS-132, was initially the last scheduled mission for Atlantis, though she would later fly STS-135, the shuttle program's final flight. The success of Atlantis illustrates meticulous engineering, careful coordination, and the courage of astronauts. The orchestration of man, machine, and controlled combustion is nothing short of breathtaking. Atlantis now resides permanently at Kennedy Space Center, Florida, a testament to the shuttle program's extraordinary power and grace. The legacy of this orbiter continues to inspire those who dream beyond our atmosphere. How do the F-35B and F-35C maintain control during vertical landings and carrier launches at Tailhook 2012? Engineers monitor every maneuver while pilots push the aircraft to its limits. The versatility between the F-35B's short takeoff and vertical landing and the F-35C's carrier capabilities is astonishing to observe. Even during brief hover tests, engineers note subtle performance shifts that reveal the aircraft's adaptability. Systems are checked continuously, with avionics and flight controls synchronized for optimal performance. Test pilots execute complex flight patterns, evaluating how each aircraft responds under stress and varying conditions. Even minor adjustments in throttle or control surfaces can change the aircraft's behavior drastically, and the crew adapts instantly. During vertical landings, the F-35B demonstrates lift fan technology, stabilizing as it descends onto simulated carrier decks. Catapult launches and arrested recoveries for the F-35C are also rigorously tested, simulating real-world naval operations. Engineers record data from hundreds of sensors, capturing every parameter, from airspeed to wing flex. Telemetry shows how minute environmental factors influence jet behavior, requiring continuous attention. It's surprising how integrated these systems are, allowing seamless interaction between pilot inputs and onboard computers. The coordination between human skill and automated systems is critical, ensuring safety while pushing the aircraft to operational extremes. Post-flight, engineers review telemetry to refine performance and identify improvements, balancing stealth, speed, and maneuverability. Crew debriefs highlight lessons learned, informing future designs and pilot training. Each takeoff and landing, each maneuver, represents a blend of cutting-edge technology and pilot expertise. The footage captures not just flight, but a symphony of aerospace engineering, human judgment, and rapid adaptation. Every data point recorded helps maintain the exacting standards expected of operational fighter jets. Audiences can appreciate the careful orchestration needed to make these jets perform reliably in challenging environments. This showcases the F-35 program's advanced capabilities, preparing pilots and engineers for operational readiness while pushing the boundaries of modern naval aviation. Safety, precision, and innovation dominate each test sequence, leaving observers with a deep respect for the craft and coordination behind these jets.
High-performance sucker cutters shape turbine blades at GF Machining Solutions. Roughing, semi-finishing, and finishing use specialized inserts for precise dimensions. Air internal and emulsion coolants control heat throughout. Every cut matters. Even small deviations impact efficiency. Foot and interface slots are machined with solid carbide cutters. The system handles long overhangs like it's nothing. Finally, blades are cut off, leaving smooth, accurate components. Engineering at its best. What enables a single DMG Mori machine to perform tasks that used to require multiple setups? Skilled operators and intelligent 5-axis machines coordinate seamlessly to complete demanding tasks. That torque handling looks stronger than expected for such compact setups. The machine's synchronized axes tackle curves and angles simultaneously, producing components ready for high-performance applications. Cutting-edge control software adjusts in real time, ensuring every surface meets exacting standards. Feels like this setup doesn't waste a single move, yet achieves flawless cuts. The innovation leader continues to redefine what's possible in 5-axis milling. The MO4 BKR blacksmith tool handles twisting multiple materials with precise mandrels for artistic metalwork. The simplicity of setup makes it accessible even without prior blacksmithing skills. The square 16 x 16 mm bar is clamped with one end held steady while the torsion head turns a 500 mm section. This long twist is one of the core tasks of the tool, and you see how the bar stays aligned even as the metal rotates. A steady pull from the drive section keeps the twist consistent across the whole segment. The feed control keeps the bar stable while rotation builds the continuous helical form needed for decorative components. Someone might compare the rotating bar to a slow mechanical coil, doing its job without hesitation. The flat 20 x 4 mm bar goes through a similar pass. Once positioned in the torsion head, the strip rotates along the same 500 mm span. The motion forms a clean longitudinal twist suitable for frameworks and forged decor. The switch from a smooth surface to a textured line happens clearly once the rotation reaches full engagement. The contrast between flat stock and twisted output shows how the tool handles two very different cross-sections without adjustment issues. You might relate the shift in shape to peeling open a ribbon that naturally curls into place. The machine then works with 4 separate bars loaded into the twisting head. The stock can be square 6 x 6 mm, 8 x 8 mm, or round EU 6 mm, depending on the set used. All 4 pieces turn together around the central axis, producing a unified twisted element. This configuration is supported by the included dies designed for multi-bar operations. The synchronized turn makes the set look like a group of lines tightening toward one center point. The final operation involves twisting 2 E8 mm bars at the same time. They are placed side by side in the torsion fixture and rotated together to form a paired twist. This step uses the tool's dual bar capability, useful for creating symmetrical forged elements. The rotation keeps both bars matched along their length. The machine completes these 4 tasks with steady motion, showing how it adapts to different stock types in one workflow.
Hermal C30U ensures aluminum engine blocks achieve extreme precision and surface quality. This kind of machining demands exact alignment at every stage. On the Hermal C30U, a model block made from ALZ NMGCU1 5 alloy undergoes the full machining process. Operators mount the 140 by 140 by 70 mm workpiece on the Gressel GRE-POS 5X clamping system, ensuring stability under a spindle power of 15 kilowatts and torque of 130 Newton meters. The speed and accuracy here are surprisingly commanding. Face milling begins on cylinder surfaces for roughing, followed by roughing the V-contour, preparing each area for final finishing. Each pass removes material efficiently without compromising surface integrity. It's fascinating how controlled this aggressive material removal can be. Cylinder face finishing, then smooth surfaces, followed by flange roughing, drilling and countersinking of M6 and M8 boreholes, and cold-forming threads for both sizes. The threads form cleanly, even under heavy-duty loads. The process continues with roughing and finishing of M36 by 1.5 boreholes, V-contour finishing for M8, housing finishing, pocket milling, and thread milling M36 by 1.5. Every milling cycle is carefully tracked by the CAM system for accuracy. You wouldn't expect all this to be completed in a single setup so efficiently. Operators constantly monitor tool wear, spindle load, and alignment, leveraging Hypermill CAD/CAM programming to optimize every path. Spindle temperature and torque are continuously logged to prevent deviations. Aerosol dry lubrication, ATS, by Rotator maintains cutting performance and surface quality throughout the operation. Even minor adjustments are automatically corrected by the machine control. As each step is executed, tolerances are maintained to meet stringent industrial standards. The combination of high spindle speed, robust clamping, and advanced programming ensures each engine block is not only dimensionally accurate, but ready for functional testing. The Hermel C30U handles complex contours with surprising stability. Beyond the technical precision, there's a sense of efficiency that makes the entire workflow feel fluid. Almost comical how smoothly the machine handles such a variety of operations. It's like the block knows where to go next. Once milling, drilling, and threading are complete, the engine block undergoes inspection before delivery, ensuring the final product aligns with quality benchmarks. Each aluminum component demonstrates the seamless integration of human oversight and machine power, illustrating how high-performance tools from MH Franken enable production at world-class standards.
See how Pete's Tire Barns in orange MA turns worn Michelin Tweel Airless skid steer tires into retreaded high-performance assets. The Tweel's polyresin spokes require careful evaluation for any cracks or deformations before retreading. The Tweel is unlike any traditional skid steer tire, using high-strength polyresin spokes instead of air to support the machine's load. Successfully retreading a Tweel required both experience and a willingness to experiment. After an initial inspection of the used Tweel, technicians buffed down the surface to remove wear and imperfections. Operators measure the surface roughness to determine the ideal buffing depth for proper tread adhesion. The buffing machine removes approximately 1 to 2 millimeters of the surface layer for optimal adhesion. The buffing process ensures that the new tread will bond correctly, avoiding weak spots that could compromise performance. Edges around the rim interface are smoothed to prevent gaps during rubber fill. Operators check the uniformity of each buffed section using calipers to maintain consistent depth. Any remaining gaps between the spokes were filled with specially formulated rubber. Rubber is layered incrementally to ensure even distribution across the spoke surfaces. This rubber is engineered to match the modulus and elasticity of the original material. This step not only reinforces the structural integrity of the tire, but also creates a smooth foundation for the new tread. It's kind of wild to see rubber filling those complex spokes. Almost looks like sculpting a tiny architectural marvel. Each filled section is lightly compressed to remove air pockets that could weaken the bond. Once the surface was ready, a new tread was carefully applied. Technicians use alignment guides to center the tread within fractions of a millimeter. The alignment had to be precise, centering perfectly over the polyresin spokes. Tread ends are overlapped slightly and pressed firmly to ensure continuous contact across the circumference. Any misalignment could have caused uneven wear or premature failure. Tread splices are inspected for adhesion and smoothness before curing. The tread ends were spliced and pressed to maintain uniform contact. The tire assembly is rotated slowly to verify that tread placement remains even before full curing. After this preparation, the assembly entered a curing process lasting over 4 hours under controlled heat and pressure. This curing step allows the rubber to fuse securely to the underlying material, forming a permanent bond that resists peeling and cracking. Curing molds are preheated to maintain consistent temperature throughout the process. The result of these steps was a retreaded tweel ready for field testing. Pete's Tire Barns plans to evaluate its performance at a local glass recycling facility, subjecting it to heavy loads, tight turns, and frequent stops. This field test will reveal whether the retreaded tweel can maintain the durability and support expected from the original Michelin design. Extending the life of such an innovative tire not only benefits customers economically, but also reduces landfill waste, aligning with environmental goals. Seeing a tweel roll out of the plant looking almost brand new is surprisingly satisfying, like a high-tech comeback story. Pete's Tire Barns. Success also highlights the value of technical expertise and adaptive processes. Standard retread methods had to be adjusted to accommodate the polyresin structure. Buffing, rubber fill, tread application, and curing all demanded careful attention. Technicians maintain a log of all heat and pressure cycles to ensure repeatability across production. With a precise process, the retreaded tweel maintains load support and flexibility while delivering a cost-effective solution. Components were selected for durability and repeatability, keeping downtime low and output consistent. High-quality molds and presses are used to maintain consistent shape during curing. This is a great example of how modern retread facilities can innovate while still relying on proven methods. Final inspection includes checking tread hardness, surface uniformity, and spoke adhesion for safety standards. By the end of the process, the wheel retains structural integrity, consistent tread depth, and the durability needed for commercial use. If you think about it, retreading a tire without air is almost like giving life to a mechanical skeleton. Crazy clever. The project demonstrates that with the right expertise and equipment, even the most unusual tire designs can enjoy a second life. Feel the transformation as worn tires at Renovado de Neumáticos Rio Pueblo get a second life. Instead of applying adhesive over the entire surface, technicians thoroughly attach each rubber layer individually. This layer-by-layer approach ensures maximum contact and adhesion between the new tread and the old tire carcass. The tire is placed on a rotating machine that slowly spins it, allowing for even application of each layer. Above, a pressing device carefully applies pressure to the fresh layer, securing it firmly to the tire. The precision of each press avoids bubbles or gaps that could compromise performance later. Once the first layer is firmly in place, the process repeats. A new strip of rubber is aligned, pressed, and bonded, building the renewed tread gradually. Operators monitor alignment and thickness continuously to maintain balance and safety standards. Each tire may undergo several passes, depending on the number of layers required to match a new tire's performance. The repetitive nature of layering demands consistent attention and hand-eye coordination, turning what seems simple into a craft. After all layers are applied, the retreaded tire is rotated several more times under pressure to consolidate the rubber and remove any residual air. Even small misalignments at this stage could affect the tire's lifespan and load-bearing capability. The result is a tire that performs like new but at a lower cost and with reduced environmental impact. Using this method, Rio Pueblo minimizes rubber waste, making each retread an eco-conscious solution. Final inspections ensure uniformity, proper bonding, and consistent tread depth around the entire tire. Testing includes rolling checks and visual inspections to confirm no defects remain. It's fascinating how a machine and careful layering can revive tires that would otherwise be discarded. Once approved, the tire is ready for service, offering durability, safety, and cost-effectiveness for operators. Each retreaded tire tells a story of craft, machinery, and sustainability working together. Layers of ABS LT13D filament rise as the LSAM 10 feet x20 machine builds a marine boat hull pattern. Each segment prints in time-lapse before the pieces are joined and machined to exact dimensions. Additive manufacturing allows such a complex hull to be ready in under 10 working days, cutting traditional tooling time dramatically. After trimming, coating, and finishing, fiberglass is cast over the pattern to create the mold. How fast a boat hull goes from digital file to physical mold. Operators guide the 120 extrusion line at IMAC McKean Limited to produce high-quality cable consistently. That feed looks faster than expected for such precision work. ISO EN 9001-2008 compliance ensures durability and performance. Hard to imagine a single line handles this smoothly. Engineers align the LSAM 10 feet x 20 machine to print the marine boat hull pattern in Tecmer Electrofill ABS LT13DP. Parts 1 through 6 are time-lapse printed, then joined and machined for precise trimming. That scale makes you realize additive manufacturing can handle massive boat tooling. After coating, a fiberglass mold is pulled from the finished hull pattern. You wouldn't expect a single machine to produce something this intricate so quickly. The complete process finishes in under 10 working days. Plastic waste is shredded and sorted to prepare for the pavement tile production. Operators feed the pieces into the melting chamber, where controlled heat turns plastic into a workable material. The melting chamber allows precise temperature control to handle different types of plastic without degradation. That amount of plastic being processed at once is more than you'd expect for small-scale tiles. The molten mix moves to the molding station, where hydraulic presses shape it into uniform pavement tiles. Excess material is trimmed and recycled back into the system. You can almost see the efficiency built into every press stroke. After molding, the tiles are cooled on conveyor belts to retain their shape and hardness. Workers inspect each batch for consistency, removing any flawed pieces. Surface texture checks ensure tiles meet slip resistance and durability standards for outdoor use. Color additives and surface texture adjustments are applied depending on the design. Once quality checks are complete, the finished pavement tiles are stacked and prepared for delivery. Kind of surprising how waste can be turned into durable construction material so quickly. Maintenance teams monitor the melting temperature and press pressure to ensure performance. This method reduces plastic pollution while creating valuable infrastructure products. That combination of sustainability and productivity really hits hard. By the end of the cycle, hundreds of uniform tiles are ready for roads, walkways, and outdoor spaces, demonstrating the potential of recycling in large-scale manufacturing.